have talked about isotope symbols, and we've talked about nuclear equations, and we've talked about some of the different kinds of radiation, and we've talked about, all this fun stuff. And now we're going to talk a little bit about an important concept in nuclear reactions, something called half-life. And our target here, we're still working on being able to predict the outcome of a nuclear reaction. So let's go ahead and talk about half-life. Okay, the half-life of an isotope is how long it takes for half of the atoms in that unstable isotope to decay, right? So to kind of demonstrate this idea, you see on the board behind me, I have 12 atoms. Let's say these are 12 atoms of some unstable isotope, and they have a half-life of some amount of time. So when I start off, they're all there. None of them have decayed. Let's say one half-life goes by. After one half-life has gone by, half of the atoms there have decayed. So how many have decayed? Well, I started with 12. One half-life goes by, half of them have decayed. So 6 have decayed, and 6 are left. So I might ask you, what fraction are left after one half-life? After one half-life, we have 1, 2, 3, 4, 5, 6 of them left out of 12, which is 1/2. So after one half-life, half of the atoms are left. What if another half-life goes by? Now I have 6 here. How many would I have left after another half-life? After 2 half-lives, how many would be left? So after another half-life, half of what I had before have now decayed. So before I had 6 left, half of those have now decayed. I have 3 left. So what fraction of the original amount remains? Right? Originally I had 12. I now have 3 left. 3 out of 12 is 1/4. 1/4. So after one half-life, I had half left. After 2 half-lives, I have 1/4 left. I don't really have enough circles up here where I can continue to cut it in half, because you can't really cut 3 in half, right? I mean, you can. It's 1 1/2. We could still do the math. It would still work out. It would still be fine. But after 3 half-lives, you should have 1/8. After 4 half-lives, you'd have 1/16. And there's a pattern here. There's a pattern in these numbers. Each of these is a power of 2, right? This is 1/2 to the first power. This is 1/2 to the second power. This is 1/2 to the third power. This is 1/2 to the fourth power. So after so many half-lives, the amount that remains is 1/2 to the power of the number of half-lives. Okay, so 2 to the whatever power, 1/2 to the however many half-lives power. So if you want to know how many or what fraction would be left after 100 half-lives, do 1/2 to the 100th power. It's that simple, right? Okay. Now, every different isotope has a different half-life. Some of them have very short half-lives, fractions of a fraction of a second. Some of them have very long half-lives, in the billions of years. Some of them have half-lives of days, or hours, or weeks, or minutes, right? It's really hard to, just from the name of an isotope, say what its half-life is going to be. They're all different amounts. Really, the only way to know is experimentally, to go and to measure how quickly the isotopes decay, right? So it's something you can look up. It's something you can look it up online. If you need to know what a half-life of a material is, I'll tell you what it is, or I'll give you the tools to figure it out, right? That said, there are a few different kinds of problems that they're going to ask us to be able to solve, okay? One of them, using this idea we just talked about, is what I call what fraction remains problem, right? So here's an example of a what fraction remains problem. It says cesium-137 has a half-life of 30 years. What fraction of the original sample would remain after 90 years? So the thing to ask yourself is how many half-lives have gone by, okay? If a half-life is 30 years, and 90 years have gone by. Well, how many times does 30 go into 90? 3 times. So there have been 3 half-lives. So to figure out what fraction remains, remember 1 over 2 to the n power, right? To the number of half-lives. Well, if the number of half-lives is 3, what's 1/2 to the 3rd power? Well, 2 to the 3rd power is 8. So what fraction remains? 1/8. Pretty simple, huh? Okay, another kind of problem they might ask us to be able to solve is what I call a how many grams remain problem. It's pretty much the same kind of problem with just one extra step. Okay, so here is a how many grams remain problem. So cesium-137 has a half-life of 30 years. The original sample was 10 grams. How much would remain after 90 years? So it's pretty much the same as the last problem. I just changed it to be a how many grams problem, right? So first thing to figure out is what fraction will be left at the end. And that's exactly what we did before. So first, to figure out the how many grams remain problem, the first thing to do is figure out what fraction remains. And then all you have to do is multiply it by that original amount. So if I'm going to have 1/8 left, and I started with 10 grams, then I'm going to do 1/8 times 10 grams. And that should come out to about 1 1/4, 1.25 grams. So that is a how many grams remain problem. Pretty simple there. Here is another variation on that same kind of problem. This is what I call a how many grams did there used to be problem, right? So cesium-137 has a half-life of 30 years. The original sample was 10 grams. How many grams would there have been 90 years ago, right? So in the past. So if they're asking you about the past, this is a how many grams did there used to be problem, right? So the first thing to figure out is how many half-lives have gone by, right? We said there was 3 half-lives, and what fraction remains? And we said it was going to be 1/8, and now it's just like the other problem, only instead of multiplying, we're going to divide because we're going back in the past, right? If you're going into the future, multiply. If you're going into the past, divide. So instead of doing 10 grams times 1/8, I'm going to do 10 grams divided by 1/8, right? And 10 grams divided by 1/8 should give you 80 grams. So back in the past, there was 80 grams. Another kind of problem they're going to ask us to figure out here is what I call the how long will it take problem, right? Here's an example. It says the half-life of isotope X is 2 years. How many years would it take for a 4-gram sample of X to decay and only have 0.5 grams of it remain? Okay. So the first thing to figure out is what fraction do we have left? So if we started with 4 grams and now we have 0.5 grams, what fraction is left? So that would be 0.5 grams over 4, which is 1/8. So 1/8 of that original amount is left. And then ask yourself, how many half-lives does that correspond to? So 1/8, like we talked about a minute ago, is 3 half-lives. Right? And then, if 3 half-lives have gone by, and the problem says that a half-life is 2 years, how many years have gone by, right? It's 2 years times 3, which is 6 years. Okay. So the how long will it take problem, first figure out what fraction you have left, how many half-lives is that, and then multiply that by the half-life. That tells you how long it would take. The last kind of variation is what I call a what is the half-life problem. So they tell us what we started with, they tell us what we end with, they tell us how much time has gone by, and they ask us to figure out what is the half-life of this isotope. So in this problem here, it says if 100 grams of gold-198 decays to 6.25 grams in 10.8 days, then what's the half-life of gold-198? Okay, so the first thing we want to figure out is what fraction is left. So we know what we started with and we know what we ended with. What fraction is left? We ended with 6.25 grams. We started with 100. And if you simplify that fraction is 1/16. Okay, so we have 1/16 the original amount left. Then ask yourself, how many half-lives have gone by? 1/16 is how many half-lives? Okay, 16 is 2 to the 4th power. So this is 4 half-lives. Okay, 4 half-lives have gone by. Now, it also says 10.8 days have gone by. So 10.8 days is 4 half-lives. So how many days are in a half-life? Well, all we have to do is divide. So we'll take those 10.8 days and divide by the 4 half-lives. 10.8 divided by 4 is 2.7. So the half-life is 2.7 days. There is a little bit about how to solve some of these problems involving half-life, right? So hopefully that helps us to be able to predict the outcome of nuclear reactions. So until next time, take it easy.